All right, so in the last video, we looked at end behavior for exponential functions, functions that involve exponential functions, rational functions, things like that. We want to turn our attention to logarithmic functions now, since that kind of goes hand in hand with exponential functions. It's a pretty appropriate follow-up. So we want to first look at the end behavior of the graph of y equals the natural log of x. And we've seen this graph before. We analyzed logarithmic functions and their graphs in the first week of the course, but this is another image of the graph of the natural logarithm. So y equals ln of x. Now, we can look at the behavior of this graph as x approaches positive infinity, but we can't look at the behavior as x approaches negative infinity, because the logarithm, the natural logarithm, is not defined for any negative values of x. It's not even defined for 0, it turns out. So we can't let x approach negative infinity if it's not even defined over there. However, we can let x approach 0 from the positive side, or from the right, because this function does approach 0 even if it doesn't ever, if x is never allowed to equal 0, and it does so coming from the right, using the positive values for x. So we can talk about both of those limits when we think about end behavior for a logarithm. Now, in this case, as x approaches positive infinity, the graph can be a little bit misleading because it appears as though the logarithm is actually leveling out. If you notice, as you go further and further to the right, the rate of growth of this curve is decreasing. The function itself is increasing, but at a slower and slower rate as we move towards the right. That's misleading because this graph actually does shoot off towards infinity. It just does so very, very slowly. So that means that the limit as x approaches infinity of the natural log of x is still just infinity. As x approaches 0 from the right, we can see that this function takes a nosedive and just starts plummeting down in the negative direction, which suggests that the limit as x approaches 0 from the right of the natural log of x is negative infinity. We can generalize this result to other logarithms. If I replace the natural log of x with any log whose base is greater than 0, so the base b is greater than 0 and not equal to 1, because we know that that's necessarily the case, then we get this same thing happening. We're not going to do much with this, but this is just something that's worth mentioning, since it's we already talked about exponential functions and their end behavior. Okay, now what we're going to do to kind of start wrapping things up is we're going to look at, since we already looked at horizontal asymptotes, we're going to return to the topic of vertical asymptotes, which again is what we get when a limit of a function as x approaches some finite number goes to either positive or negative infinity. That's when the graph shoots off towards infinity or shoots down towards negative infinity, creating a vertical asymptote. And we've already kind of seen this in the previous section. Any one of these limits implies a vertical asymptote at C. Notice we have one-sided limits and a two-sided limits down here. So any one of these would imply a vertical asymptote. So what I would like to do is determine the vertical asymptotes of a function here, using this as a guide. So I would like to first look at this expression here, and notice we're not told what value of x we should be approaching. So an important thing to remember when it comes to vertical asymptotes is, let's suppose this is not the graph of this function, but just as an example, let's suppose that you do have a vertical asymptote at some value c, maybe something like this, right? The function itself will not be defined at c, because if I could plug a number in for c, then I would have a point somewhere on this dashed line. But the fact that it's a dashed line is the way we indicate graphically that there are no points on the curve that intersect that line. So the function cannot be defined where a vertical asymptote is appearing. It can only approach that. So when I come over here and I look at my function, I have to determine where this function is undefined, because wherever it's undefined is where we're going to find vertical asymptotes. Okay, so I can find where it's undefined by writing this as x minus 3 over x minus 3 times x plus 3. I'm factoring the denominator because it's a difference of squares, okay? So looking in my denominator, I could say that this is undefined at x equals plus or minus 3. So what I should be doing is I should be looking at what's happening as x approaches positive 3 or negative 3. I'm going to look at both of those limits, okay? Let's start with the limit as x approaches positive 3. And I'm going to start with just the original function itself, x minus 3, like before factoring it, because who knows? I mean, maybe that's all I need. Maybe all I need is this. Being the limit as x approaches a finite number now, so this is like the types of limits we've been dealing with before this section. We know that limits can be brought up into the numerator and denominator of a quotient like this only as long as the denominator itself is not equal to 0 when I do that. But I can see that if I plug 3 in using the direct substitution property, I do get a 0 in my denominator. In fact, I also get a 0 in my numerator. So that's one of those 0 over 0 indeterminate forms. Those limits might exist, they might not, but we don't know what it is until we simplify this a little bit. So here's where I would do the factoring. Limit as x goes to 3 of x minus 3 over x minus 3 times x plus 3. And now I can see that these x minus 3's are in fact going to cancel. Okay? And I get 1 over x plus 3 here. All right, so having canceled these out, this limit exists because now I no longer have that 0 over 0 indeterminate form. And my denominator specifically is not going to be 0, so I can use direct substitution. I can plug 3 directly in, and I get 1/6 as a result. Okay, so this is finite. This limit is not taking my function to infinity or negative infinity, which needs to happen for a vertical asymptote. That tells me that there is no vertical asymptote at 3. Now something else is happening at 3, but we're going to talk about that next. Let's then look at the limit as x approaches negative 3. And it turns out we're going to have to be a little bit more specific. We'll have to look at one-sided limits, but for now, let's just think about a two-sided limit. So again, if I wanted to do this, x minus 3 over x squared minus 9, I would once again run into this issue where my denominator is coming out to 0 if I try direct substitution. Negative 3 squared is 9, minus 9, that's 0. But this time, if I try direct substitution in my numerator, I'm going to get negative 3 minus 3, which is not 0. That's negative 6. So what we have is a non-zero number over 0. And as we have seen previously, these types of limits always go to either positive or negative infinity. So what I need to do is determine which of those two it is. What I'm going to do is simplify this limit. We've already done the work to simplify it over here. So I'm going to do that next. 1 over x plus 3. Now I can see a little bit more clearly what's going on. Again, this is 1 over 0 if I were to plug negative 3 in. But I'm not supposed to plug it directly in. I'm thinking of this in the context of limits. So x is approaching negative 3. It's not equal to negative 3. Okay? At this point, I would need to determine whether this is going towards positive infinity or negative infinity. And in fact, it depends on which direction we're coming from as we approach negative 3. So let's modify this and say, let's make it a one-sided limit where we're approaching from the right, okay? Remember, that means we're approaching negative 3 using numbers that are larger than negative 3. So what helps is to pick a number that's close to negative 3, but just slightly smaller or slightly larger. Negative 2.9 is larger than negative 3. So we're working this out in our head. If you plug negative 2.9 in for x, negative 2.9 plus 3 is 0.1. It's positive. In fact, any number that's greater than negative 3, when I add a 3 to it, I will get something that's positive. So positive 1 over some positive number that I think of as a very very small in the sense of being close to 0, that would give me a positive infinity there. Okay? If I approach from the other direction, so same thing, x minus 3 over x squared minus 9. I can simplify the expression to make the limit easier to evaluate. 1 over x plus 3 again. In this case, I'm approaching from the left, which means I want to use a number that's smaller than -3, but close to it to get a sense of what's happening with this limit. So something like -3.1 would be less than -3. If I put a -3.1 in for x here, I would get -0.1. And 1, which is positive, over -0.1 would give me some negative number. That suggests negative infinity. Now, whether we get positive or negative infinity, in either of these cases, that implies that there is a vertical asymptote there. So I can say that there's a vertical asymptote. I have a tendency to just abbreviate VA for that. And it's at x equals -3. It's important that you don't just write -3. Vertical asymptotes are lines, and lines are represented using equations, not just a number. Specifically, vertical lines will always look like x equals some constant. That's what you should be writing, not just -3. Okay? So we only ended up with one vertical asymptote here. All right. Now, in the previous example, the one that we just did, we made a note of the fact that the function was undefined at x equals 3, but there wasn't a vertical asymptote there. And really what had happened is that x minus 3 that we got when we factored our denominator canceled with the x minus 3 in the numerator. And so that sort of disappeared from our evaluation of those limits. But it's still important to make a note of the fact that that limit, or that value of x equals 3, is not in the domain of that function. Because when we graph a function, we have to make sure to exclude any points who have x values that don't belong to the domain. So how do we deal with that? Well, here we want to determine what this example is sort of illustrating what's going to happen. Same function, y equals x minus 3 over x squared minus 9. Wherever we're getting a place where a graph is not defined and there's not a vertical asymptote, at least in the case of these rational expressions, what you're going to get is a hole in the graph. And we've seen, since we've been talking about limits, examples of graphs that have holes in them, and this is how they can occur, is from, a term canceling out. So we already saw that the limit as x approaches 3 of x minus 3 over x squared minus 9 is equal to 1/6. And again, just for reference, we did that right here, okay? That, we don't need to go through the work again since we already did it, but this tells me that it's a two-sided limit, so I should see both parts of my curve as x approaches 3. They should both be approaching this y value, but there shouldn't be an actual point there. So that means that there is a hole there. And the hole occurs at the position of a point. In this case, 3 would be the x-coordinate, because as we approach 3, that's where we're getting close to that hole. The y value is 1/6. Okay, so notice the coordinates of that hole, the x-coordinate comes from whatever x is approaching here. The y-coordinate comes from the result of that limit. So for reference, here is the graph of the function that we just dealt with in the last two examples. You can see where my vertical asymptote is. That's right there at x equals 3, -3, sorry, x equals -3. And you can see a hole in the graph right there. And it's not hard to verify, but maybe in the video it's not as easy to see these grid lines. That does occur at 3/1/6. That's where the location of that is. So that was one example illustrating how to find vertical asymptotes in holes, but we can talk about a general strategy for doing this. So here's how we approach finding holes in vertical asymptotes, specifically when we're looking at rational functions, which is what that was. First, you want to factor your numerator and denominator, and then divide out any common factors. Some examples, you may already have the numerator and denominator factored for you, but you still need to divide out any common factors. The factors in the denominator that divide completely will determine the holes. And then we set each factor in the denominator that divides completely equal to 0 to find the x value of that whole. Okay? The factors that remain in the denominator, and only in the denominator, are the ones that determine the vertical asymptotes. So remember, that's what's left after canceling things out. Anything that is still sticking around in your denominator is going to give you a vertical asymptote. And so we, again, set each factor that remains in the denominator equal to 0 to find the x value of the vertical asymptote. One thing that's missing from this description is how to get the y coordinate of a whole. Remember, it tells you where the x coordinate is, but it doesn't tell you how to find the y coordinate. Going back to our previous example, we found that here by taking the limit as x approaches that specific x value where the whole occurs and getting this as my y value. Now, we can actually make this a little bit more streamlined because if you notice, evaluating this limit was actually just a matter of plugging 3 directly in. We got to use the direct substitution property. So we can frame this without mentioning limits at all. If you have a rational expression, and you factor it like we did here, whatever cancels out, x minus 3 for example, set that equal to 0 and solve it for x. That part is described on the second page. But then whatever number you get from doing that, plug that back into the simplified version of that rational expression to get the corresponding y value. That's what we did here. We represented that with limits, but we didn't actually need a limit here to be able to do that. So to close things out, let's do an example where we want to find vertical asymptotes and wholes. We're not going to graph this function. It's a good exercise to go into Desmos if you've tried that yet and plug this in to see what this graph looks like, because then you can verify that we've done things correctly here. But all I want to do is locate those vertical asymptotes in those wholes. So looking at my function here, it's very complicated looking, but we have the convenience of it already being factored for us. That's really helpful. So I'm going to look through here and see if anything cancels out. I get x minus 1s canceling out. And I also get x minus 5s canceling out. So that tells me I'm going to get wholes at x minus 5 equals 0 and x minus 1 equals 0. We would want to solve each of these for x. So that's x equals 5 and x equals 1. Typically, you don't even need to write this, right? Because hopefully by now you can look at the x minus 5 here and think, without writing it down, if I set that equal to 0, then x would have to be 5. That you should have that on automatic already. Okay, so we know we're going to get wholes at these x values, but we haven't figured out the y coordinates of those wholes yet. The next step we want to do is rewrite what's left here after everything has been simplified. So I'm going to have 4x squared times x minus 2 over, in my denominator, I have 2x plus 1, and that's it. That's actually the only thing left in my denominator. So I don't really need those parentheses there, but I already drew them. Okay, so at this point, I know that whatever is left in my denominator, whatever factors are left, I would want to set those equal to 0. So vertical asymptote at 2x plus 1 equals 0. And then I want to solve this. That's an easy one to solve. Subtract 1 and then divide by 2. X is equal to negative 1/2. So right away I have my vertical asymptote. X equals negative 1/2. But now I want to revisit the wholes and figure out the y coordinates of those wholes. So I need to take these x values, plug them back into this simplified version of my expression here, my function, and I should no longer get zeros in the denominator because those have canceled out, those factors that do that. So let's start with x equals 5. If I plug x equals 5 into this function, I'm going to have 4 times 5 squared times 5 minus 2 all over 2 times 5 plus 1. 5 squared is 25 times 4, that's 100. 5 minus 2 is 3. 3 times 100 would be 300. So that's 300, and then this is going to come out to 11 in my denominator. Leave that in that form. Leave it as a fraction. That's fine. Next, plug in x equals 1. Okay, so same thing. Plug 1 in for all of the x's. 4 times 1 squared times 1 minus 2 all over 2 times 1 plus 1. So again, this is a good mental math exercise. 1 squared is 1 times 4, that's 4. 1 minus 2 is negative 1, so when I have this 4 and this negative 1 and I multiply them, I get negative 4. In my denominator, 2 times 1 is 2, plus 1, that's 3, negative 4/3. All right, so I've done a bunch of work. Let's summarize our results. So I have a vertical asymptote at x equals negative 1/2. It's okay to use this shorthand, at least for homework and stuff. I know what VA stands for. That's obviously an at symbol. So this tells me vertical asymptote at that line right there. Holes at, remember the holes they occur at points in the plane, and we have x coordinates and y coordinates for those points now. So when x was equal to 5, my y coordinate was 311ths. So I would put those together into a point. 5, 300 over 11. And then when x was equal to 1, my y coordinate ended up being negative 4/3. That is how we present the location of those holes. You want to have both coordinates in there. Okay, that's going to be it for section 1.3.